welcome back. We're going to be looking at geometric series and geometric sums today. So in order to do that, of course, we're going to have to look at a few things and think a little outside the box this time. This does get a little bit tricky, so if at any time it's too fast, just pause the film and try and catch up, and then restart it. So let's get started. We're going to have a little chessboard here. It has 64 squares, and what we're going to do is put down one piece of wheat on the first one. This is a very old story. I don't know if it's apocryphal or not, but supposedly there was a king that wanted to reward one of his faithful servants that had solved a big problem for him, and he said, name your reward. And the guy said, well, take a chessboard, put down 1 grain of wheat on the first one. Then on the next one, put down 2. And then on the next one, 4. And so on until you get to the last one. And that will be my reward. And the king was thinking, geez, what a good deal. That's going to be easy to pay. Until you start to realize that, these numbers start getting really big, really fast. And our job is to figure out how to add all this up in a simple way and get a general formula so that we can solve a problem that is of the same character. So we're going to be looking at a geometric series, which this is, and we're going to then look at how do we solve a general geometric sum. How do we add that series up? So this is a particular case, but each case can then be solved in a similar way using the same formula. Okay, so what happens here? After 8 grains of wheat, I just couldn't use little dots anymore. I had to actually use numbers. And it continues. Now I'm going to switch the numbers into this, because we're going to need this different way of writing it in order to create later the series and then the sum. So I really haven't done that much. This still has a value of 1. Remember that 2 to the 0 is 1, and 1 times 1 is 1. And this, it's 1 times 2, because 2 to the 1 is 2. So that's 2. Now this is 1 times 4, and this is 1 times 8, which is 8, and so on. So we get 16 there, and it just continues. But down here, we're glad that we switched to the new way, because good luck writing this down. Good luck having a calculator that can print out the first, 20 places or something. It would not be easy to put that number in the standard form. We got to have something to make it fit. That is a very big number down there. All right, that being said, I'm going to take another step now. And now I'm going to basically give each square a name. And in math, we usually have names that are, well, not very fun sounding, but useful. So the name of the first square is going to be A index 1. Okay, so A1. That's right here. Here's A1. A2 will be right next door to it. And we'll just keep going until we get to the very last one. Now, you'll see that it'll start to make sense now why I did a 1 times 2 to the 0 and 1 times 2 to the power of 1 and so on. And that's because you'll be able to see a pattern now. See, A2 is going to be whatever A1 was, and we didn't have to start with 1. The guy could have said, start with 2 grains of wheat and then double it. So A1 in this case is easy. It happens to be 1. And the K happens to be 2, because 2 is the one that keeps getting squared and then cubed and so on. So every time we get to a new square, we multiply it by another K. In this case, the first time, the K doesn't do anything because it's to the power of 0. But it does something in the second square because when it's to the power of 1, it is what k is. So here's the second square, 2 times 1. The third square, we get 1 times 2 times 2, and that's what that is. So now we can use letters to create the general series. And as we go all the way down, we're going to see that when we get to the bottom spot there, we'll be able to put it in. We know we have 64 squares total, okay? And that's what n is. N is 64 all the way down here. But it's 64 minus 1, so we'll get 1 times 2 to the 63. Now that makes sense because we know that the very first square, the power to which 2 is raised is 0. Then you go to 1 and 2 and 3 and so on as it continues down the series. So now we know the value of each individual square, and that can be useful. We might want to know that in some circumstances. But the reward for the servant of the king was going to be the sum of each and every square. So we're not quite done. We will need this, but we're not quite done. So let's take a look at some more ideas here. How would we add this all up? Well, first, what does it mean to add it all up? Well, we're going to have 64 squares, okay? The first square has a value of 1. Second square, value of 2. 4, 8, and so on until we get to the last one, and who knows what we're going to call that number. But big it is. Okay, so that's the idea. But let's use the new terms where we used a and k and stuff. Let's see what happens when we do that instead. Okay. The sum is going to be the first square, the second square, and so on. You just keep going until you get to the very last square. Okay, that's the idea in the general term. And if you don't remember what this means, a dot dot dot, that's just continue as you were doing until you get to the last spot. Okay, so we've done that now. This is the idea, but you know, if you were to do this by hand, it would be just awful. So what we're going to try and do is manipulate our way out of it. And the first thing to do, and it may or may not be completely obvious, but this is a classic problem. So this is how it's been done for a very long time. So let's look at it. What can we do? Well, the first thing is multiply the left side and the right side by k. So every single term in this yellow line there will be multiplied by k. And this is what happens. Okay, so in other words, Sn times k gives you that. A1 times k gives you this. And so on, and so on, okay? We're not done, not by a long shot, but now we can start to manipulate again. So the next step will be to take this bottom line here and subtract what's above it. So the left side there will take away the k, we'll have ksn, and we'll take away sn. And then we'll have term by term by term, and we'll see what we can do with it. So I've prepared some stuff, so let's take a look at it. Okay. If you first look at just the right side, you'll see that some of the terms are identical. So the things in the blue box, okay, that's the same thing. And it was the bottom take away the top. So this will eat up that. It goes away. And that goes away. And that goes away. And every single thing except for this and this get crossed out in the same way. And you can say, well, what about that? Well, yeah, this represents the step just before you get to here. And why is that? Let me just clean up a bit here. You see, the k to the power of n minus 1, well, just think of it this way. If n was 10, this would be k to the 9. And if n still is 10, then this becomes well, that's k to the 10. A1 is just A1. So k to the 10 is there. This one doesn't go away. But what comes right before that? You get A1 times k to the n minus 1. Because if this is 10 there, k to the 10, then what came just before it? K to the 9. And that's what that one would represent. So no matter how far out you go until you get to the very last square, the only survivors of this are going to be this term and this term on the right side, and then we'll have ksn minus sn. So that cleans up to this. Here you can see in the amber box, we still have on the left side, we just have to write it out. But on the right side, all the terms in between disappeared. The only thing left is this, and that's right there. And it's minus because it was the bottom minus the top. And then this one, which is the very last term there. So that cleans up really nice. And this is a lot easier to handle than trying to manually add 64 of those boxes together. But we're not done. We can still do a bit more. Now that we've cleaned up a bit, we can factor out the common terms. And here they are. Okay, so we factor out the Sn, we get that one there, and on the right side we factor out the A1. Okay, when that's done, we can then take another step, because what we're interested in is just this. So let's manipulate it a bit algebraically. And then we get this nice general equation for the summation of a geometric series. And now we can say, all right, let's use this and find out how much wheat we actually have. So let's take that little green thing, put it up, and we'll fill in the little boxes, all the little variables. What do we know? We know what A1 is. That's 1. We know how many squares there are. There's 64. So you put that there. We also know what K is. K was 2. That was because K is the thing that is the part of this that grows multiplied by 2 and then by another 2 and another 2 and another 2. K is that particular term. And then downstairs it's still k minus 1, and k minus 1 is just 1. So the bottom part isn't going to do anything at all. And then it cleans up to this absolutely huge number. And it's so big that it turns out to be about 1,500 times the amount of wheat that we grow in a year on the entire planet right now. So if this had happened a couple hundred years ago or 1,000 years ago, there's no way the planet could have produced that much wheat. So the king was very frustrated and killed the guy. So be careful what you ask for. Well, I hope that helps. I'll be coming up with another movie to show you how to do the geometric sum when it comes to interest rates soon. All right, see you next time.